These are notes on endothermic and exothermic reactions. It's part of our new unit, which is thermochemistry, essentially the heat involved in chemical reactions. And these notes come from 17.1 and 17.2 in your book. So first, a little review, kind of some terms that we maybe haven't seen in a while, just so that you get a good scope of what we're looking at here. The first one is temperature, capital T, which is the average kinetic energy of a system. In gas laws, we were mostly working with Kelvin. We had to change everything to Kelvin. In thermochemistry, you may remember, from when we did things like Q equals Cm delta T, we can stay in degrees Celsius. Heat, do you remember Q from Q equals Cm delta T? Heat is represented by the letter Q, lowercase q, and it's energy that transfers between two systems because of a difference in temperature. So you could have two things that are at the same temperature. There's not going to be any heat between them. There's not going to be any energy transfer between them because they're at the same temperature, even though one may have more energy than another, total energy, due to there being a larger quantity of it. So heat, remember, transfers from warmer things to colder things. So on a cold day, if you open your door, assuming your house is heated, the energy will flow from your house to the outside. On a hot day, where maybe if you have air conditioning on inside, if you open your door, the energy is going to flow from the outside, the warmer, to the inside. And then specific heat capacity, lowercase c, is the amount of energy needed to raise 1 gram of a substance by 1 degree Celsius. So those are all terms that we've seen before, but we're going to bring back in this unit. So you want to make sure that you have re-looked at those. If you're looking for where you can find this stuff in your book, it's also in Chapter 17. So let's look back again. We're still kind of in the review phase, but now we're going to bring in some new ideas at Q equals Cm delta T and Q equals N delta H of fusion or vaporization. You maybe remember these from when we did phase change. And we're going to look more closely at this concept of delta H. So H is what's called the enthalpy of a system. So that's a new word for a lot of you. And enthalpy is the heat content at constant pressure. So in all of these, we're assuming we are not changing the pressure of a system. Delta H, then, is the heat in kilojoules either released or absorbed by a reaction. And that is then the change in enthalpy. Delta meaning change, H meaning enthalpy, so delta H is the change in enthalpy. And Q, which is heat, the energy transferred between two systems, or within a system, equals delta H. So you can use those two terms equally. You could say the enthalpy change, or you could say the heat. So now let's look at endothermic and exothermic reactions, and we can break these down. Exo meaning to go out, so for example, an exit, you go out. Endo meaning to come in, an entrance, you come in. Thermic meaning some sort of enthalpy change or heat transfer. So these are reactions that deal with a change in energy. And most reactions do. I can't off the top of my head think of one where the delta H is 0. I'm sure there is one out there somewhere. So first, two perspectives. The first one is going to be the system. The system is the part of the universe that you're focusing on. So if you're talking about some water freezing, for example, the system is simply your cup of water. If you're talking about energy within a house. The system could be your entire house. It could be the rooms of your house or whatever. So the system could be as big or small as your focus is, but that the system is part of the universe. It's not the whole thing. And obviously what takes place within the system may affect what takes place outside of the system, but maybe that's not what you're focusing on. And then the second part is, or the second perspective is the surroundings. So it's the area directly around the system. So let's say you're looking at cooling a bowl of hot soup. The system is the bowl of hot soup. You're looking at that. The surroundings are literally kind of the air surrounding that. So, for example, let's take the bowl of hot soup and let's say you're in the kitchen. The surroundings are the air directly around the bowl of hot soup. Now, those are obviously, that area, the surroundings, may have a heat change, which may lead to a temperature change, because they're in contact with the soup. But for example, your next door neighbor's kitchen is not going to be affected by your soup in your kitchen. That's not part of the surroundings. These are pretty basic terms to understand. The system's what you're focusing on. The surroundings are the area around your system. But we need them in order to understand everything we're talking about with endothermic and exothermic reactions. So endothermic reactions are reactions in which the system absorbs heat from the surroundings. And you can think of that as heat is a reactant. So in order for this reaction to occur, you need heat from the surroundings. And in that case, delta H, your enthalpy, is positive. It's a positive number. And I'm going to show you some graphs next. And so endo, remember we said meant entrance. So there is an entrance of energy into the system in an endothermic reaction. On the opposite end of the spectrum, we have exothermic reactions in which the system loses heat to the surrounding. So the system is giving off energy to the surrounding, and you end up with heat as a product in that case, and delta H enthalpy is in that case negative, so exactly the opposite. So exo, we talked about exit meaning to go out, so heat is given off to the surroundings. And as you may remember from when we did MC delta T at the beginning of the year, Q equals negative Q. So in an endothermic reaction, however much heat the system absorbs is the amount of heat the surrounding loses. In an exothermic reaction, however much heat the system loses is the amount of heat that the surroundings gain. So here are some energy diagrams, and there's a couple of things in these diagrams that we need some background information on. So the first is this weird thing here called activation energy. And you'll notice it's in both diagrams. Activation energy is essentially the energy needed for the reaction to proceed. So every reaction out there has some sort of activation energy that the reactants need to reach that level before the reaction can proceed, before reactants can turn to products. And going back to what we talked about with the manganese oxide in the rocket lab, how manganese oxide was a catalyst, what a catalyst does is it lowers this activation energy. So, you know, maybe instead of your activation energy here, the activation energy is only here, and because of that, then the reaction can proceed a lot faster. So here, this is energy, the potential energy of your reactants and products. And so if here are your reactants, and once you get over that activation energy, the energy of your products are down here, you can see that that's lower than this. And so therefore, that's going to be an exothermic reaction. You're going to give off, that reaction will release this much energy. And that's why exothermic reactions, your delta H is negative, because the energy of the products is less than the energy of the reactants. And we'll talk about what that energy is a little later in class. But basically, it takes energy to break reactants apart, and then it releases energy to form products. So if that release of energy is more than the amount of energy needed to break those reactants apart, you get an exothermic reaction. Here we have our reactants down here, so at a much lower energy. And once they're up over the activation energy, let's say our products are here. So again, it takes energy to break reactants apart, and energy is released. You can see there is definitely a release of energy as the products are formed, but those end products have more energy than the reactants. Therefore, this is the amount of energy they absorb. So in both cases, the reactants, it took energy to break those reactants apart, and then energy was released upon formation of the products. But in this case, once the products were formed, they were at a lower energy than the reactants had been. Therefore, they released energy, and delta H was negative. Here, however, the products were at a higher energy than the reactants, so this much energy was absorbed, and so delta H was positive. Now, this is true of chemical reactions, but it can also be true of physical changes as well, such as phase change. So here are some things we've already talked about, and bringing back in that vaporization and fusion, and then here, if we're condensing, it would just be negative H of vaporization, and freezing would be negative H of fusion. And then we have sublimation, going directly from solid to gas, and deposition, going directly from gas to solid. And this actually was a chart I took offline, and it had a great arrow here that said enthalpy, but they had misspelled the word enthalpy, so I took that arrow out and just put in here we have low enthalpy, here we have high enthalpy. And so you'll notice that solids, well, let's say this, liquids are at higher enthalpy than solids, meaning these reactions are endothermic, that the energy of the product is higher than the energy of the reactant. It takes energy to do that. In other words, energy is lost from the surroundings in order to make that reaction proceed. The system gains energy, the surroundings lose energy. The same when you vaporize, you go from liquid to gas. The system gains energy. Where does it gain it from? The surroundings. The surroundings lose energy. That's why evaporation, we say, is a cooling process, not because the gas loses energy, but the surroundings lose energy. That's why when you sweat and that sweat evaporates, you end up cooler. The opposite is true on this side. These are exothermic reactions. The enthalpy of the liquid is less than that of the gas, and so you lose energy as you go from gas to liquid. Where does that energy from the system go? Into the surroundings. That's why a steam burn is so painful, because you've got gas that is condensing on you. As it condenses, it releases that energy, which goes into you to burn you. That's also why your refrigerator or your freezer have to keep turning on as things are freezing, because it removes energy from the system, from the liquid. Where does that energy go? Into the surroundings. In a freezer, that is the freezer, so that warms up. The motor has to kick on to remove that heat. So hopefully that's kind of tying everything back together and introducing some new concepts as well. And then we'll talk about this a little more in class.